Welcome to Squeezing Out of the TX Box, Rheological Evolution of Volcanic Lavas, Impact Lavas and Cryolavas by Alan Whittington, Aaron Morrison and Alexander Sehlke. Normally I'd show a nice field or lab photo, but this has been my life for the past 3 months. Quite a lot of what I'll show comes from the PhD dissertation of Aaron Morrison, work in progress. So what is the TX box? In igneous petrology, we learned that lava starts to crystallize at the liquidus and reaches 100% crystallization at the solidus. Yet many volcanic rocks contain glass, and sometimes lavas cool all the way to the glass transition with little or no crystallization. The glass transition is typically around 700 to 750 degrees for dry melts, but can be lower than 300 degrees C for hydropegmatitic melts. Volcanism on Earth is typically restricted to compositions that can be generated by partial melting of Earth's mantle and or crust, and through subsequent modifying processes such as magma mixing, assimilation, and fractional crystallization. This leads to the familiar range of terrestrial lava compositions, limited at the present day to phoidites, for example Nyiragongo, at the low silica end, and high silica rhyolites, for example Obsidian Dome, at the other. The most voluminous lava type on Earth is mid-ocean ridge basalt, MORB, at intermediate silica content but much lower alkali contents. We can go beyond these ranges. So impact melts are composed primarily of target material whose composition is dictated by surface processes that extend beyond the realm of igneous petrology. Consequently, they span a much wider compositional range. On terrestrial bodies with primary crusts, such as the anorthositic lunar highlands, impact melts can resemble monomineralic melts, which could never form by any other mechanism. Where impacts remelt secondary crusts, for example the lunar mare, the same magma could be reborn, but at a much higher temperature than during its initial formation and then placement. There are other mechanisms for heating lavas above their liquidus temperatures, for example isothermal ascent of hydrous magmas or viscous heating. Silicate volcanism has been important on most terrestrial bodies that have differentiated internally and continues to the present day on Earth and also Io, where lava is suspected to be much hotter than on Earth and hence more mafic, with komatiite, somewhere down here in picrobasalt, a popular candidate composition. Io also exhibits sulfur volcanism. There are also non-silicate lavas on the Earth, such as carbonatites. Measuring lava rheology. Melt rheology can be studied by a number of methods, but two of the most popular for lavas are concentric cylinder and the parallel plate or uniaxial creep technique. Viscosity is the ratio of the applied stress or torque to the resulting strain rate with units of Pascal seconds. Viscosity for a given melt can vary by many orders of magnitude as a function of temperature. Each measurement technique typically spans a range of a few log units, which leaves a gap in the middle as seen in the diagram on the right. In this case, the gap is mostly to do with the range where silicate melts crystallize during the measurement, but we can interpolate between the two sets of measurements on the liquid, one at high temperature, one at low temperature. Polymerized melt compositions such as rhyolite are both more viscous and more Arrhenian than the depolymerized melts such as basalt. The difference is greater when accounting for the lower eruption temperatures of silicic lavas and higher eruption temperatures of basaltic lavas, indicated by the filled circles. This is why basaltic lavas frequently occur as rivers of fire, while the photo in the top right is a view of a cliff exposing the top few meters of a very thick obsidian flow, about 50 meters thick. Crystallization occurs during cooling in many lavas to varying degrees, but rarely to completion. Crystallization causes the effective viscosity to increase rapidly, mostly due to the physical effect of crystals impeding flow. The effect is strongly nonlinear with increasing crystal content. Secondary effects on viscosity can result from changing liquid composition, potentially including devolatilization. There are two end-member curves, one for equilibrium crystallization, the green one that we learned about in petrology class, favoured by slow cooling, and the other for complete suppression of crystallization to produce a glass. The faster cooling occurs, the lower the temperature at which crystallization begins. When considering lavas, the rapid increase in viscosity accompanying crystallization indicates a change in flow morphology, for example the well-known Pahoehoe to A'a transition in basaltic lavas. Abrupt increases in viscosity will result in sharp decreases in flow velocity, potentially including complete cessation of flow advance. Here we see three possible lunar impact melts, including the anorthosite that falls outside both the temperature and composition ranges of terrestrial magmatism, shown in red there. These melt sheets would have been emplaced at temperatures in the range 1500 to 2000 degrees or even higher, where viscosities for all three lava types are actually all quite similar at around 1 Pascal second. During emplacement, viscosities would have remained below about 10 Pascal seconds until crystallization began at different temperatures for each melt. Equilibrium viscosity of JSC1 increases by 80 times from 80 Pascal seconds at 1320 degrees to 633 Pascal seconds at 1200 degrees C. Crystallization also results in non-Newtonian behavior with an apparent yield strength near 500 Pascal seconds inferred at 1200 degrees C. At lower temperatures, cryovolcanism has been cited as a likely mechanism for the extrusion of sodium carbonate-rich material on Ceres. Sulfates, chlorides, and carbonates are likely cryovolcanic materials at Europa, Enceladus, and other ocean worlds. Note that this diagram uses a log scale for temperature on the x-axis. Most lavas, whether silicate, carbonatite, or cryolava, are erupted at viscosities between olive oil, about 0.1 Pascal seconds, and ketchup, about 100 Pascal seconds. Their subsequent evolution depends on their thermal history, which in turn depends strongly on lava morphology. For example, well-insulated tubes, or open channels with brecciated crusts that expose the flow interior. One really important question is to what extent morphology can reveal rheology, and to what extent that can reveal composition or crystallinity. Comparing the apparently similar morphology of Moralia Chaos on Europa, top right, with Obsidian Dome on Earth, bottom right, suggests common emplacement styles, despite the factor of 100 difference in scale and a factor of nearly 1 trillion in viscosity at eruption. Looking to the future, as planetary geology reaches the edges of the solar system and prepares for the leap to exoplanets, we should be ready to encounter volcanic processes occurring over a much wider range of TX space than we are familiar with. At the same time, viscosity is going to stay within the same 15 orders of magnitude range that we are currently used to, between the consistencies of water and glass. This still leaves plenty of room for further research. 3 key areas would be 2 and 3 phase lava rheology. Can we bridge the gap between analog and high temperature studies? Relating flow morphology to rheology, are similar features necessarily formed in similar ways? And what are the likely compositions of exoplanetary lavas? Thanks for your time. For comments and questions, please contact alan.whittington@utsa.edu.